All right, welcome back. After that quiz, hopefully it was enough of a wake-up call. Here we're going to take a look at our final lessons. And I say plural because it turns out we're going to divide this into two separate lessons to finish up the trig unit. This is math from the void, where math comes at you out of nowhere, and the unit circle is the portal to our destinations. All right, this is officially part 15, since we're including the pop quiz. And we're going to look at some more types of problems. It's just a single type that you would encounter involving trigonometry, or some situations that you would have to, that you might come across that are trigonometric in nature. How to answer these types of questions. I see some inverses. This -1 exponent, when you're dealing with trig stuff, is representing the inverse function. Sine inverse, cosine inverse. There's even tan inverse, but I don't see any tan inverse problems here. Let's take a look at the inverse trig ranges. And if you're not familiar with these, I have a whole video on inverse trig and understanding inverse trig. So you should go check that out. The range of the inverse function is going to spit out basically a range of angles which would solve the equation sine of theta equals whatever the x value is. So in this case, sine inverse of -√2/2, that means we're looking for a theta. We're not looking for x. We're looking for a theta such that sine of theta is equal to -√2/2, which requires the unit circle knowledge. So if that didn't kick your butt enough earlier, we're back looking at unit circle stuff. Now the range for cosine inverse stretches from angle 0 to pi. I won't get into why. I'll talk about that in a different video. Go check it out if you want to. And tan inverse follows the same pattern as sine inverse. So we go from -pi/2 to pi/2. Okay, let's see how that's going to help us with some of these. Now we're finding the exact answer. That usually means don't use a calculator, don't get the decimal approximation. We want the exact answer. And we're going to do this in radians, okay? So when is sine equal to -rad2/2? Since sine is the y value on the unit circle, and rad2/2 is in the pi/4 family, we're going to be looking at this angle here, and we're going to call it -pi/4 rather than calling it 7pi/4. Because the range of sine inverse is from -pi/2 to pi/2. 7pi/4 is not in that range. Okay, great. Let's take a look at this. Cosine inverse of sine of 4pi/3. So we work from the inside out. Let's find out what sine of 4pi/3 is. That's in the pi/3 family, and 4pi/3 is right there. So this is going to be negative, and since it's in the pi/3 family, we have rad3/2. And so now we're looking for the cosine inverse of -rad3/2. Rad3/2 for cosine, that would be in the pi/6 family, but we want it to be negative. So it has to be here, and that would be 5pi/6. That is within the range of cosine inverse, which is from 0 to pi. Okay, easy enough. And let's move through this one. Sine inverse of sine, it does in a sense cancel, but we have to be careful because the sine inverse of anything cannot be equal to 4pi/3. This is not in the range of sine inverse. So we're not able to use 4pi/3. Let's look at where 4pi/3 is located. It's located down here. Where else do we have a sine value that is the exact same as that sine value? It's going to be here in the fourth quadrant. So this is going to be at 5pi/3, but 5pi/3 is not in the range of sine inverse, so we're going to call this -pi/3. When we're doing sine inverse, we look at the angle from range -pi/2 to pi/2. So this is an angle of -pi/3. Okay, easy enough. Let's keep it moving. The tangent of the cosine inverse of 3 over 4. Now, here's something where we do not have a unit circle value. No unit circle value. No nice one, anyways. Oops. Now I made it italicized and underlined for some reason. There we go. For 3. That's still italicized. That's fine. For 3 over 4. So we have to draw a triangle. And we're going to draw a triangle in the quadrants according to the range of the cosine inverse. Right? So we're going to draw this triangle in the first quadrant. And cosine inverse is telling us that we have a sum angle such that the cosine is equal to 3 over 4. This is not a 3, 4, 5 triangle. Do not fall for it. If you fell for it, I tricked you. This is not a 3, 4, 5 triangle. Can't make mistakes like that in the void. There's serious consequences. Now we're going to have to find this missing value. Let's just call it y. And we know that 3 squared plus y squared is 4 squared. So therefore y squared equals 16 minus 3 squared, which is 9. And so y is equal to plus or minus root 7, technically, but on this case, it's going upwards, so this is our plus root 7. Why did we need that? We needed that because we don't want just the angle, theta. This is equal to theta. We want tangent of that angle, which is why we draw the triangle, right? This is a right triangle, and we drew it so that we can use the tangent ratio, SOH-CAH-TOA, opposite over adjacent. So tan of theta is simply going to be equal to the opposite side we established as square root of 7 over the adjacent side of 3. Really not bad at all, guys. This shouldn't be entirely challenging if you've already learned this information before. Hopefully it's still relatively fresh, so we're not like founding any new ideas or principles, and we're not planting any new seeds and having to water them. We're just pruning, right? We're pruning your skills and revealing the buds, the flowers that are underneath it, so that we can really use them to maximum capacity once we get to calculus. All right, and here is a slightly irregular use of the inverse, but it's an algebraic use of the inverse. Oftentimes you'll get a quiz question, or sometimes you'll get a test question like this. It says to evaluate the expression. We're going to use a similar idea that we did in the previous problem. It's just that we have some letters involved. That's okay. Don't be scared of that. Here is the inverse symbol, which means we should draw a triangle. And there's no need to assume that it's negative. I don't see that z is negative, so let's just draw it in the positive space. Doesn't have to be to scale, doesn't have to be proportional, none of that. It's just a simple diagram so we can label sides. Sine is the ratio of the opposite to the hypotenuse. So that means this is indicated as z, and this is square root of z squared plus 3. Kind of looks like a 7, so I'm going to fix that. Z squared plus 3. Now it just looks like a weird like slug or like Jabba the Hutt or something. Anyways, we want to find the tangent of this angle. Again, this whole thing is theta. I have now drawn the triangle because that shows me theta right there. I want the tangent of theta. So that means I want the opposite over the adjacent. I don't have the adjacent side right now. So I can use the Pythagorean theorem, right? I can say that, let's call this x. I can say that x squared plus z squared equals, I'll write this out very carefully for everybody, the square root of z squared plus 3 squared. So a squared plus b squared equals c squared. Nothing new, Pythagorean theorem. That means x squared plus z squared. Yes, you could have just removed the root. I'm just showing my work more carefully. And so x squared equals 3. Therefore, x equals, technically, plus or minus square root 3 are considerations, and then we're just going to say it's positive because we put it in the first quadrant. We had freedom to put it in the first quadrant because, oops, getting ahead of myself. We had freedom to put it in the first quadrant because there was no need to assume that this was a negative ratio. And now we can do tangent of theta. Opposite over adjacent. And if you really want to fix it, you can call it 3. Wait, what would you call that? I guess if you would do root 3 on the top and the bottom, yeah, you would have root 3z over 3. That is also acceptable. See, so you can use inverses with variable expressions, and you can still calculate tangent, cosine, cosecant, cotangent, even if you want to. But the point of this exercise was to show you what kinds of problems you can get. And we're going to wrap things up in the next lesson with solving trigonometric equations. So here's a heads up to review some of your identities. If you don't have any identities written down anywhere, or you can't find them, it's probably a good idea to write them down again. You won't need all of them. You'll just need sum and difference identities, Pythagorean identities, double angle identities. These are good ones to have on hand. Nothing too crazy. Back to the void.